Today we're working on the sliding window questions from the LeetCode roadmap. So it's these 6 questions right here. Sliding window questions are usually done in the same way. Usually we take a small window, which is consecutive elements, from something like an array or a string, and then we see that there's a left side and a right side. So we can move the right side to make the window larger or the left side to make the window smaller. This is usually done so we have an O of n solution to iterate through all possible things like substrings or subarrays that have a certain attribute or quality. So first let's take a look at a simple question, best time to buy and sell stock. So in this question we're given an array prices. Prices I is the price of a given stock, and we want to maximize the profit by choosing one day to buy the stock and a different day to sell the stock. So in example 1 here, we can choose day 2 at index 1. So we buy it at price 1, we can sell it later at price 6 for a profit of 5. Although price is higher on the first day, we can't buy the stock before the first day, so there's no way to sell it for 7. So in the next example, the price of the stock is going down, so there's no way to make a profit from there. So in this question, we want an O of n approach because price's length goes up to 10 to the power of 5. So we want to iterate through this array once. In this question, all we have to track is the smallest price, because at every price in the future, we just check what's the best time we could have bought the stock. For example, at 5, the best time we could have bought it is at 1. And that's the same thing for everything, for every single day in the future. So every day in the future, we just care about what's the best day we could have bought it in the past, and then we're going to sell it at this current time. We're going to see what the best day it is to sell in the future. So here let's write some variables. The answer is 0, so we assume we can't make any profit at the start, and min price equals to prices of 0. So min price is something we're going to track as we iterate through the array. So for price and prices, so suppose we're at a price, how much money can we make? Profit, the profit is going to be the current price minus the minimum price we could have bought it at. We're going to set answer to be the maximum of answer or profit. So if profit is greater than answer is going to be profit. After that, we're going to set the min price to check if the current one is actually the minimum. So min price equals to min price, or price the current price. So in the end, we're going to return answer. So going through example 1 here, for price and prices, we're going to check, hey, can we make any profit from 7? For example, 7 minus the min price, which is currently at 7. So we can't make any profit there, so that's 0. And at 1, can we make any profit there? We can't, but the minimum price is going to be set to 1. And in all future days, for example, 5, at 5, we can make a profit of 4 because 5 minus min price is going to be 4. 3 minus min price is going to be 2. 6 minus min price is going to be 5. So after we're done iterating the array, we see that 6 minus 1 gives the maximum profit, and we're going to return that as the answer. So let's try running that. Nice, okay, it worked. So this is a sliding window approach because the left side of the window is the minimum price, while the right side of the window is what we're currently at, so the price. So this question worked. It was a pretty simple and pretty standard sliding window problem. But we don't actually track the entire window. So in the next question, we're going to track the entire window here. So longest substring without repeating characters. Given a string S, we want to find the longest substring. A substring is consecutive, and it does not have repeating characters. So for example, in the first case here, ABC is a valid substring because it's consecutive and it does not have any repeating characters. ABCA, sorry, I highlighted B there. So ABCA is actually not valid because it has repeating characters A. So basically we want a consecutive substring that has unique elements. And to do that, we should be using the sliding window method. Let's create some variables. L equals to 0. L is the left side of the window, and we're going to be iterating through the right side of the window. We should also declare an answer for the longest length of the substring. So for r in range len s, so for every possible index in the string, we're going to use r as the variable to represent the index, the right side of the window. So for example, if R was 0, 1, 2, then the substring would be A, B, C. To track what's in this window, we want to use a counter. So in Python, a counter is basically a dictionary, but it's specifically designed to count the instances of things. For example, in this case, we're counting the instances of every character appearing. So counter S of R. S of R is the character we're currently at. So we're going to add that to the counter. So starting from 0, we're going to add A to the counter and then add B and so on. So while counter, so we're going to check, we want to check if the counter has any duplicate elements. So the only element that could be duplicate is the element we just added, because before this, we're always going to make sure the counter has unique elements. So while counter S of R is greater than 1, so there's more than one instance of the character S at R. This is a repeating character, so we can't have that. So we're going to move the left side of the substring up 1. So the left side, remember, is at the L index. So counter S of L is going to minus equal 1. So when we move the window up, for example, if the window included A before and now it doesn't, we're going to decrease A from the counter. And A is the character at S of L. And then we're going to move the left side up, L plus equals to 1. So as long as there's a duplicate, we need to be moving L up and decreasing the counter to remove the first element in the window. So we can check, so now this is valid. This is a substring without repeating characters. So we're going to put that into answer. Answer equals to max answer, or R minus L plus 1. R minus L plus 1 is the length of the current sliding window. So in the end, we can just return answer. Nice, okay, that worked. So let's try submitting it. So this solution is an O of N approach. We're only iterating through the string a single time, and the space complexity is going to be constant because there's only 26 different English letters. Actually, no, there could be digits and symbols and spaces. But that is a finite amount, so the space is basically constant. So let's move on to the next question, longest repeating character replacement. So you're given a string S and an integer K. You can choose any character of the string and change it to any uppercase English character. And you can perform this operation at most K times. So return the length of the longest substring containing the same letter you can get after performing the above operations. So in this case, we want a longest substring containing the same letter. So we want all A's or all B's. K equals 2. That means we can change 2 letters in this string. For example, we can change all the A's to B, so B, 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 and that's in length of 4. Or we can change the A's to B's to A's and have A, 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 which is also length of 4. So in the next case, we can, for example, here, we can change this B in the highlighted substring to be A, so there's 4 A's. Or we can change this A in the highlighted, I highlighted the wrong thing here, change the highlighted A to a B and return B, 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 so also a length 4. So the idea behind this question is we want a substring where there are, so in each sliding window, there's a character that appears the most. For example, here, the character that appears the most is B. So the length of the substring minus the character that appears the most is the characters that we need to replace. So as long as the number of characters we need to replace is less than K, we're able to replace that. So let's code this up in this very similar sliding window approach. L equals to 0, answer equals to 0, and we're going to create a counter, which is just a dictionary. So for R in range len S, again, we're going through every single index in the string S. We're going to increase the counter S of R, plus equals to 1. So the condition here is while we want to see what the maximum element of the counter is, basically the character that is appearing the most times. So the syntax to do that in Python with a counter is counter dot most common, most underscore common, and 0. Actually, no, it's 1. So 1 means the first most common character. That's all we care about. Index 0, index 1. I'm going to explain what these indexes mean in a second. So this is the number of times the most common character appears. So while the most common and the length of the string, the sliding window, is going to be r minus l plus 1. So this is how many characters we have to change as long as this is less than k. So while this is greater than k, which is problematic, we're going to move l up by 1. Oops, it should be l minus equals to 1. Okay, let's explain the most common things. So for example, if we have a counter for candies, for example, something like jelly bean 3, so that means there's 3 jelly beans, and there are, for example, 2 lollipops. So this is a counter for candy. So when we do counter, let's call this candy counter. When we do candy counter dot most common, we can choose how many things we want. So for example, if we do 2, we return the top 2 most common elements. If we do top most common 1, we only return the most common 1. So when we return it, it's going to be in the form of an array. So it'll return something like jelly bean. So if we want the first most common element, it'll be jelly bean 3. So in this case, we want the first element, which is this tuple here. So we're going to call element of 0, and then we want the number of times jelly bean appears. So that's going to be index 1. That's why we have this index 0, index 1 thing after counter.most common. So with that out of the way, we can say if, so as long as the length of the array minus the length of the window minus the number of most common instances is greater than k, we need to decrease the counter by 1. So we can replace all the non-most common characters with the most common character. And answer is going to equal to max answer or the length. So r minus l plus 1. After that, we can just return the answer. Let's try running it. Nice, okay, that worked. So this solution, again, is O of n. The space complexity is constant because we just keep a counter, and the counter has at most 26 elements because there's 26 uppercase characters in English. And counter.most common, this is implemented with a priority queue, but because we only have 26 elements, it's basically constant time. So that was this question. And let's move on to the next one. So permutation in string. Given 2 strings s1 and s2, we want to return true if s2 contains a permutation of s1 or false otherwise. So let's look at the example to make that a little bit more clear. So s1 is ab. So what are the permutations of ab? It's a, b, and ba. So does s2 contain ab or ba? It does. It contains an instance of ba. So we should return true in this case. In the second example, s1 equals ab again. So the permutations are again ab or ba. But s2 doesn't contain any substring that is ab or ba. For example, b and a, they're separated by an o. So in the case of example 2, we're going to return false. So in this question, we can quickly notice that we only care about substrings in S2 that are the same length as the substring S1. So we only care about substrings of length 2, for example, EI, ID, and DB, and so on. Because if it's a length 3, that's guaranteed not going to be the same permutation. That's not going to be a permutation of S1. So let's create some variables. Let's let len1 be the length of S1 just so it's easier to type. And we want to create a counter to count the elements of S2 up until a certain point, up until it reaches the length of S1. So counter equals to counter S2 0 all the way until len1 minus 1. We do len1 minus 1, so we have the element. So this goes up until the element e, and then in our loop later, we can check the element I and add it to the counter. So for r in range len s2, but we also don't want r to start from 0 because, for example, if s1 is longer, we would only want to start from the end of s1. So let's start from len 1 minus 1 all the way until len s2. So the r again is the right side of the window here. So counter of s at r is going to increase by 1. So if counter equals to counter s1, let's declare this a variable so we don't have to call counter construction methods every time. So let's call this the goal is going to be a counter of s1. So if the counter that we have currently is equal to the goal, we want to return true. We found a permutation of s1. However, if not, we should return false at the end. So after increasing s of r, the counter, the right side by 1, we want to decrease the left side by 1. So we move the window down the string. So counter s of l should minus equal to 1. And that should do it for this question. Let's try running it. S is not defined, right? This is S2. And I did not declare L because we don't have L. So L should always equal to R minus len 1 plus 1. So basically, for example, if R is equal to I here, so R is 1, then L should be the first element. So we move down the length of L1, so move down 2, and then plus 1, so we get 0. So let's try running this again. Cool, okay, that worked. Let's try submitting it. And this question, again, is O of n, linear time. The space complexity is also constant. We only keep one counter. The counter is the length of string 1, so that's constant. Sorry, that's not constant, that's based on the length of S1, so it's also an O of n space complexity. And yeah, that worked. So moving on to the next question. We're given two strings s and t. They have lengths m and n respectively, and we want the minimum substring of s such that every character in t, including duplicate characters, are included in the window. So if there isn't a substring, we return the empty substring. So in this question, they make it so that the answer is always going to be unique. In example 1 here, we have t_abc. This is our goal. We want a substring in s that contains all the characters abc at least once. So here we can see that the shortest one is going to be ba and c, that contains abc, and it happens to be the shortest. Another one contains abc as well, but this is longer than ba and c. So example 2 and example 3 are pretty straightforward. Example 2, a contains a, so that's just the answer. And in example 3, t is longer than s, so it's impossible for s to contain all the characters in t. So we return the empty substring. Basically, we can't find anything. So here, very similar to the previous questions, we can set the same variables l equals to 0, and our counter, we can set answer is going to equal to s. So we're going to find a shorter substring than s to contain t. We're going to have a counter equal to counter. This is what we have currently. And goal. Goal is the counter of all the elements inside t. This is just like what we did before. So we also need to define a helper function. So how do we see that every character in t is covered by the counter we have so far? So let's write a helper function, defines covers. So covers takes in our current counter and also takes in our goal counter. So for every character, so for character and count in goal.items, So this enumerates all the values inside goal. Character is the character itself, and count is how many times that character appears. So if the current counter for that character is less than the desired count, we're going to return false. This does not cover. Otherwise, we can return true. So with this helper function, it becomes a lot more straightforward. For r in range len s, just like we did before, we iterate all the right sides of the window. Counter s of r plus equals to 1. So we increment the element at s of r by 1. So while this is a cover basically says every element in the counter, every element in T is included in the counter. So while covers, counter is our current counter and goal is unchanging, it's always the goal counter. Ans is going to be equal to s of from left all the way to r plus 1 because substring doesn't include the last character. So we need to do one more than r. And after that, we can try for a shorter one. How do we try for a shorter one? Well, we're going to move the left index, so L, up. So counter S of L. We drop the element at L, minus equals to 1, and move L up by 1. So we try to see if this new window covers. If it does, we move L up again by 1 to get an even shorter one. So in the end, we can return answer. However, answer here, we always want the shortest answer, so we should only set answer to the current sliding window if r minus L plus 1, so that's the length of answer, is less than the length of answer. Otherwise, it should just be that current answer. And it's not always guaranteed that we have a solution in S. So a trick we can do is return answer if the length of answer is less than or equal to the length of S. Otherwise, we just return nothing. So what this is doing is that we return answer. If answer is less than S, we can increment answer by 1. So this is, let's create a character that's not in S or T. So this is an impossible answer. So this answer is S plus an underscore. This is never going to happen. We're never going to get this answer. So if the length of this answer is not less than length of S, that means we didn't find it. We're still sitting at the impossible answer here. So that in that case, we'll return the empty substring. Otherwise, we'll return answer because the length of answer is less or than or equal to the length of S. So let's try running that. Nice, okay, that worked. So I did this trick at the end because, for example, looking at test case 2 here, S and T are identical. So we need the entirety of S to cover T. That's why we need answer to be longer than S at the start, just giving an impossible answer. So that if the answer, we know we found it if the length of the answer is less than or equal to the length of S. So let's try submitting that. Nice, that worked. So to simplify this a bit, because it might be a little bit confusing, we can do a variable found equals to false. So if we reach a cover, then found equals to true. So instead of doing this if else, so if found, return answer, otherwise return the empty substring. We also need to declare answer here. We should just do S plus the underscore. So that's a little bit easier, and that should also work. Let's try submitting it. Cool. Okay, so moving on to the last question, sliding window maximum. So you are given an array of integers nums, and there is a sliding window of size k, which is moving from the very left of the array to the very right. So in this example, we have k equals to 3, so we have the window 1, 3, -1, and then we move on to 3, 1, -3, and -1, -3, and 5, and so on. So there's only k numbers in this window, and each time the sliding window moves right by 1 position. So return the max sliding window, which is the maximum element inside the sliding window made into an array. So this example does it pretty nicely. So first, in this first position, the maximum element is going to be 3. So we're going to append 3 to our answer. In the next position, the maximum element is still 3. So we're going to append 3 to the answer again. In the next window, the maximum element is 5. 3 is out of the array, we have some negative numbers, and 5 is the largest one. So we append 5 to the array. So in the end, we're going to create a maximum sliding window array, and it's going to be 3, 3, 5, 5, 6, 7. So in this question, it's not very like the previous permutation sliding window questions where we can just declare a left and a right and then see if there's any attributes we can do to shorten the array. So this question, we're going to use the help of a monotonic stack or monotonic queue, because in a monotonic stack or queue, we're just going to use dequeue. Dequeue can be popped from the left or the right, so we need this to be a dequeue. All we care about is the maximum element we've seen and how many times we can use it. So for example, here we saw 3 at the position 2. We'll call this position the second position, 1 indexed. So that means we can use 3 2 times. We'll use it once, and we'll use it again in the second one. So now we see the element 5. We can use the element 5 3 times. Once immediately as we see it, next when it's in the middle, and next when it's at the start. So once it's at the start, we have an even better element 6. So we can use the element 6 3 times as well. We can always use them k times, and then until it gets overridden by 7. So we realize that we don't care about elements inside this window if a element after it is larger than it. This 1 does not matter anymore because 3 is always larger than it, and 3 is going to last longer than it. So we can just disregard it. That's why we have a monotonically increasing queue. So let's just write. So in a mono queue, we're going to have elements 3, 2, negative 1, 1. So what 3, 2 means is that we have the element 3 and we can use it twice. So once here and then once when it's at the first element. And negative 1 is the element that appears after 3. So although it's negative, it could be better than even more negative numbers. So we're going to still have to record it. And we'll only use it once because it's going to be used after 3. So we need to define a way to insert into the monoqueue because it's not just as simple as pushing to the back of it. So let's define insert queue, and we insert a number called val. So the number of times we can use something, it's at least 1 because we can always use it at least once. So we need to make sure the queue is not empty when doing comparison. So while len queue is greater than 0 and val is greater than q negative 1, 0. So negative 1 means it's the last element. So for example, here we have our queue looking like 3, 2. So that means we have the element 3, we can use it twice. And then we're inserting a new element, which is negative 1. So we see, hey, is negative 1 better than 3? Can we just replace 3 altogether? We can't. So because val is not greater than q. So but suppose we're inserting something even better, we're inserting 5. So 5 is greater than q negative 1. Q negative 1 is the last element of the queue, 0 is the first index. So 5 is better than 3. So what do? We can use 5 at least one time plus the number of times 3 is used because we basically replace all the 3's with 5's. So times plus equals to q negative 1, 1. The first index, q negative 1 is the last element in the queue, and 1 is the index referring to the number of times it can be used. So now we can pop, because 5 dominates 3, so we can pop 3 from the queue. And now we need to append 5, so q dot append, and we're going to append this as a list. Val is 5, for example, and times the times it's going to be used. So after that, we can actually create the monoqueue and start iterating. So first, let's go through nums k minus 1 times. So for I in range k minus 1, we're doing k minus 1 to get all the elements before we actually start a valid sliding window. So we're going to get the elements 1 and 3. because we're going to get -1 later, and then we're going to actually compare the elements to see which one's the largest. So let's get the elements before we reach a valid window, which is in range k-1. Insert monoq and nums of I. So we inserted every element before a valid window. Now let's start inserting from the actual window. So let's create an answer array, and for I in range k-1, so we're starting at k-1 and going all the way until the len nums, which is the last element in nums. So we're going to insert. So here, for example, we're inserting -1 into the monoq, like we explained earlier. Monoq nums. So we inserted it, so we now have a valid sliding window of length k. So how do we get the maximum value from the sliding window? We wanted to get it in O of 1 time. So this is going to be just the first element, because we always wanted the largest element. It would have dominated the previous elements and then increased the number of times it could be used. So it'll be monoq 0, so that's the first element, and 0, referring to which element it is. So now after we inserted the new element, we need to pop the previous element to get ready to insert the next new element. So if monoq -0, 1, so 0 is again 3, 1 is the number of times it can be used. So if the number of times it can be used is greater than 1 still, we want to decrement it by 1. 0, 1 minus equals to 1. However, if it can only be used once, we already just used it, so we're going to pop this and remove it from the monoq forever. Monoq 0, 1. We don't need to do that, sorry. We just pop the left element. I think pop left is the way to pop the left thing from a DQ in Python. And after that, we can just return our answer. Let's see if that works. I think pop left is the right syntax. Okay, we cannot, append is spelled with an extra D. And okay. Okay, so after clearing the syntax errors, we have the right answer here. So like we've explained earlier, basically all we're doing is keeping track of the largest number and how many times it could be used. If we have a smaller number after it, that's okay, but if we have a larger number after it, then that, for example, 5 is larger than 3, then 5 should just take over all the times 3 could be used. And again, like 6 and 7, 7 should take over the number of times 6 can be used. And then whenever we want to add to the answer, we should use that number 1 time. So we decrement the uses by 1, or when the uses remains to be 1, so we can only use it 1 more time. We've already used it, so we pop left and remove that element from the queue. So this is going to be an O of n approach. We iterate through the the nums array a single time, and every time appending or dropping elements from the monoq should be constant time. So there is a while loop here, which might make you think it's longer than constant time because it's a while loop inside of a for loop, but all we're doing is checking how many elements are in front of it, and that should be very little. So let's try submitting this. Cool. So thank you guys for watching. Hope that was clear, and I'll see you in the next video.